Hello students, welcome back. From now onwards, the discussion of solid state will become even more interesting. Now we are going to learn about the basic building block of any solid, that is unit cell, and we are also going to discuss about crystal lattices. Okay, so let's start the discussion. So now we are going to start the crystal lattices and unit cell, a very important concept for JEE purpose for all of the competitive exams also. So the real solid state is going to start from here. So get ready for that. So first we are going to discuss about the crystal lattices and unit cells. So first we will discuss what is a crystal lattice, what is meant by a crystal lattice, and then we will discuss what is unit cell and what is its importance. Okay, so let's start. So a crystal lattice is a regular 3D arrangement of points in space. It is a regular 3D arrangement of points. So you can see in this figure. So this is one point, second other point. So the points here shown, these spheres, small spheres. So here these points are arranged in 3-dimensional fashion. Okay, so they are arranged 3-dimensionally in space. So as a whole we call it as a crystal lattice. Okay, we call it as a crystal lattice. So crystal lattice is simply a regular 3D arrangement of points in space. Okay, so here each particle is depicted as a point. So each particle, the particle may be atom, it may be a molecule, it may be an ion. Okay, so if you see in ionic solids, the particle is ions, the particles are ions. So in molecular solids, the particles are molecules. Okay, so it may be, the particle may be, the solid is made up of either atoms or molecules or ions. Okay, so each particle is depicted as a point. So this point, this point, this point, like that. Okay, so each particle is depicted as a point in the 3D arrangement of the constituent particles. So if we arrange these so how many ways we can arrange these points in 3D? So this is the question, right? So how many ways, how many possible arrangements are possible in 3D? Okay, so there's a French mathematician whose name is Bravais. He is the first person who described that there are only 14 possible 3-dimensional lattices. There are only 14 3-dimensional lattices are possible. Remember, only 14. And these lattices are known as Bravais lattices. Okay, so the 14 possible 3-dimensional lattices which are described by Bravais are known as Bravais lattices. Okay, so let's see some of the important characteristics of crystal lattices. Now we are going into more details of crystal lattices. So first important point is, each point in a lattice is called lattice point or lattice site. So you will see after, in many books they call like they use the terms like lattice site and lattice point. So a lattice point or lattice site is nothing but it is a point in a lattice. So in a crystal lattice, the example, in this figure, it is a crystal lattice. So this crystal lattice, each point, so this is a point, so this is a point, this is a point. So each point is known as a lattice point or a lattice site. Okay, and the second important characteristic is, each point in a crystal lattice represents one constituent particle. So which may be an atom, which may be a molecule, or which may be an ion. As I said already, that the particle may be atom, or it may be molecule, which is a group of atom, or which may be an ion. Okay, so each point in a crystal lattice represents one constituent particle. Okay, so particles are atoms or molecules or ions. So this is one more important thing. And the third one is, the lattice points are joined by straight lines to bring out the geometry of the lattice. So here if you see, the lattice points are joined, right? In the image that I shown before, the lattice points are joined by straight lines. We are using the straight lines, and that is giving out a geometry. Before it is giving out a cubic geometry, right? So if the particles are arranged in some other fashion, so if you join those particles by straight lines, it may give out some other geometry. So they are joined by straight lines to give out a geometry for the lattice. So these three are very, very important points you have to remember, you have to understand as far as a crystal lattice is considered. Okay. So I am repeating once again these things. So each point is known as a lattice point or a lattice site, and each point in a crystal lattice represents a constituent particle. Okay. And these lattice points are joined together to bring out the geometry of the lattice. So these three are important characteristics. Now let us move to the concept of unit cell. So what is a unit cell? Which is a very, very important thing. Unit cell, which is a very, very important thing, and you need to understand this particular thing clearly in order to understand the rest of solid state. Okay. So be focused. So unit cell is nothing but it is the smallest portion of a crystal lattice, which when repeated itself in different directions will generate the entire lattice. Okay. So one analogous example I will give you. If you take a wall, right? If you take a wall, you know that wall is made up of bricks, right? So if I take this is a brick, and we use a number of bricks one over the other, one beside the other to build a wall. So we are using one more brick above this and beside this, and so on. We are arranging these bricks in a 2D or 3D pattern in building, in making a wall. Okay. So here if I ask you what is the smallest unit in this wall, so that is my one brick, right? One brick. So that brick is the smallest unit, and that smallest unit is repeating itself in this direction, in above and below, and it is as a whole it is making a wall, right? So the similar thing happens here also. So unit cell, it is the smallest portion of a crystal lattice. So we know that crystal lattice is a 3D arrangement of points, right? So this crystal lattice is formed by unit cells, right? Like a wall is formed by a brick, a crystal lattice is formed by unit cells, and unit cell itself is the smallest portion, and you cannot find a portion which is even smaller than the unit cell itself. So which is a basic repeating unit. Okay. So which when repeats in different directions. If it repeats in x, y and z directions, we'll get a 3D arrangement, and that 3D arrangement is nothing but our crystal lattice. Okay. That will generate the entire lattice. So what you need to understand here is the unit cell is the basic repeating unit, and this unit cell, if it repeats in 3D space, will get a crystal lattice is going to be formed. Okay. So a unit cell is characterized by 6 parameters. 6 parameters are used to characterize a unit cell. So let's see what are those 6 parameters. Yeah, you can see in this figure, this is a typical unit cell, and here you will see it has 3 edges and it has 3 angles, right? So it is characterized by its dimensions along 3 edges. So this is one edge, A is one edge, B is other edge, C is the third edge. Okay. So A, B, C are the 3 edges it has, and these 3 edges need not to be perpendicular to each other. Okay. So they may not be mutually perpendicular. So in some unit cells they are perpendicular, and in some unit cells they are not. Okay. So put this thing in inverted commas, a very important thing. They may be perpendicular and they may not be. So now we have three parameters. And what are the other 3 parameters? The other 3 parameters are nothing but the angle between the edges. So here see alpha, this is alpha, So this is alpha. Alpha is the angle between edge B and C, right? And beta is the angle between A and C, and gamma is the angle between A and B. Okay. So we have three edges and we have three angles. So totally we have 6 parameters, and these 6 parameters will characterize our unit cell. Okay. A, B, C are the edges, and alpha, beta, gamma are the angles between the edges. Okay. So a unit cell is characterized by these 6 parameters. Okay. So now we will go into more details of that. So let us see how many types of unit cell are possible. How many types of unit cell are we have. So yeah, in this picture you can see a unit cell is of two types. One is primitive unit cell, another is centered unit cell. So the primitive unit cell contains the particles only at the corners, right? It contains particles only at the corners. So if I take a cube, so let's suppose this is a cube. This is a cube. So the primitive unit cell contains the particles only at the corners. So it has 8 corners. So particles are only present at 8 corners. But the other is centered unit cell, and the centered unit cell contains particles not only at the corners but also at other positions. So we have particles at corners, but other than this we also have particles present at some other positions. So depending upon the positions at which the particles present, the centered unit cell is again further divided into 3 types. One is body centered, other is face centered, and third one is end centered. Okay. So these 3 are very, very important. So carefully understand these 3 unit cells, okay, that I am going to discuss in my next slides. So first one, let's see the primitive unit cell. Okay. So we know that in primitive unit cell we have lattice points present only at the corners. As I said before, we have particles present only at the corners, and is known as a simple or a primitive or a basic unit cell. So 3 names are given. We can call it as a simple unit cell, or a primitive unit cell, or a basic unit cell. Okay. So you can see we have particles present only at the corners. We don't have particles at any other positions. And a crystal lattice having the primitive unit cell is called simple crystal lattice. Okay. So if I make a crystal lattice from a number of unit cells, so whatever the crystal lattice I got from this unit cell, and that crystal lattice is known as simple crystal lattice. Okay. So a crystal lattice formed by primitive unit cell is known as simple crystal lattice. Okay. Yeah. Okay. You can also see more pictures. So this is, you can see the particles present only at the corners, and this is known as space filling simple cubic. That means this represents the actual arrangement of the particles. This is how the particles are actually arranged in reality. So you can see this is one particle. So total we have 8 particles, and if we join the corners of these 8 particles, we are getting a simple cubic. Okay. Yeah, this is the simplest way, and this is the space filling model, and this is the square array layering. That means, like, if you keep on adding the particles, like in the right side, left side, above and below, we will get a crystal lattice. Okay. And that is known as simple crystal lattice. So this is about the simple unit cell. The next thing is the body centered cubic unit cell. Body centered. So body centered. So this unit cell has particles not only at the corners but also at the center of the body. At the center of the body. Okay, let's see. Let me show you a picture. So here you can see we have particles present at corners. So total we have 1, 2, 3, 4, 5, 6, 7, 8 particles that are present at the corners, and we also have a particle where you can see a big sphere which is present at the center of the body, right? Yeah, you can also see here. There's one more extra particle we have that is present at the corner. Okay. So such type of unit cell is known as body centered unit cell, and here in this picture you can see this is how the particles are actually touching each other. So the corner particles are not touching. Observe here, this corner particle is not touching with any other corner particle, but only the particles are touching along the body diagonal. So if you see, this is a body diagonal, that is this one, this is a body diagonal, and the particles are actually touching each other along the body diagonal, and if you see all these particles, if I take all these particles are of similar size, same size, so this is radius and this is 2r and this is r, so total distance is 4r, right? Total distance is 4r, which is equal to this distance, that is related with the edge length, right? So this is A. So what will be this length? It will be root 3a, this distance. So here 4r is equals to root 3a. This is the relationship between the radius of the particle with the edge length of the body centered unit cell. Okay. So later we will also derive this thing. So but now I just want to give you an idea that how the particles are actually touching each other in a BCC. Okay. So let's move to next unit cell, that is a FCC. It's also very important unit cell. So what you need to observe is where the particles are present and how they are touching each other. This is what you need to observe here. So in face centered, we have particles present at the corners, that is there, but additionally we have particles present at the face center of each face, at the center of each face. Okay. So here you can see we have particles present at the corners, and we also have particles present at the center of each face. You can see here, yeah, this is one face, this is one particle, and the exactly opposite face is this one, and this is one more particle, and this is one particle, this is one particle, this is one, and this is one. So total we have 6 particles, right, that are present at the center of the 6 faces, and additionally we have at the corners. Okay. This is the unit cell, FCC unit cell, and this you can see, this is the space filling model, the actual arrangement of the particles, and here the particles are touching each other along the face diagonal, that is this one. So this is how the particles are touching. The corner particles are not touching to each other, but the particle which is present at the face, each face is touching with the corners at opposite ends. Okay. So this is a face diagonal and this is a face diagonal. So if this is A and if this is A, so this will be root 2a. So root 2a will become equal to, if I take the particles of same size, so this is 4r is equals to root 2a. So this is how the radius of the particle is related with the edge length of the FCC unit cell. Okay. So this is about FCC unit cell. So next is end-centered unit cell. End-centered cubic unit cell is simple. What it has is, it has the particles at the corners, but it has particles present at the center of any two opposite phases. So if particle is present here, the one particle is present here, then one more particle is present at exactly opposite face. Okay. But only two phases. We have particles present only at the center of two opposite phases, not all phases. If they are present at all center of all phases, then it will become face centered. But since it is end centered, the particles are present only in any two opposite phases. Okay. This is known as end centered unit cell. Okay. So this is about the 4 unit cells we have, and yeah, this is where you can see I will quickly summarize the things. So this is the primitive or cubic. Just observe how the particles are arranged and how they are touching each other. So this is the body center, we have particle at center, and this is the phase center, we have particles at the center of each phase. Okay. So this is about the crystal lattices and unit cells. So students, in this part we learned about crystal lattices, and we also discussed how many types of crystal lattices we have all in all, and we also discussed about unit cell and the types of unit cell, and in that we learned about simple cubic, body centered cubic, face centered cubic and Ncentered cubic unit cell. So now it is the time to learn about the number of atom belongs to one particular unit cell in a crystal lattice. So let's discuss more about this in our next part. So keep watching.